What about the imaginary axis? Here I have poles that neither have a negative real part nor a positive real part. Poles on the imaginary axis are special because they are corresponding inverse Laplace transforms, that is to say, they are corresponding impulse responses. Neither converge to zero as time increases, nor diverge to infinity as time increases. A pole at the origin has an impulse response that is a Heaviside function. It does not go to zero, it does not diverge to infinity, it is bounded. A pair of complex conjugate poles on the imaginary axis corresponds to an impulse response which is sinusoidal. Again, this is a bounded function. It neither converges to zero as time increases nor diverges to infinity. We will call these poles marginally stable poles. But notice that for the impulse responses to be bounded, these poles have to be simple. If I have two poles at the origin, the impulse response already diverges to infinity. The same happens with three poles at the origin, and so on. The same also happens for multiple complex conjugate poles on the imaginary axis. Let us sum up the classification of poles. Poles are stable on this side of the imaginary axis if they have a negative real part. They are unstable on this side of the imaginary axis if they have a positive real part. And if they are on the imaginary axis, they are marginally stable if they are simple. They are already unstable if they are multiple. As to the stability of systems, they are stable if and only if all poles are stable. They are marginally stable if there are no unstable poles, and there is one marginally stable pole or more. And a system is unstable if there are one or more unstable poles. Remember, a single unstable pole suffices to make the system unstable.